My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So, good evening to all. Hope you are well and safe from Corona pandemic. So, all we know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. So, we have to start our online program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, has already started its online program, and we have also started International Physics webinar. And I'm happy to share with you all that we have successfully completed our 113 International Physics webinar. Today it's our 114 International Physics webinar. So we are trying to adjust with this new normal situation. So today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics, Indian Institute of Technology, IIT Kharagpur, India, in physics. And we have with us today Dr. Sayan Sir, Professor, Department of Physics, Indian Institute of Technology, Kharagpur, India, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening and welcome
Good
to our
evening, yes.
International
Yes.
Physics webinar. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation. So for those who are new, I'd like to introduce our speaker with all of you. So first of all, we'll introduce our speaker, and then our speaker will deliver his speech, and at the end, we have a discussion time. Anybody can join with us and at that time. So I think you have already come to know the title of this today's International Physics webinar. And title is the Physics with Spring and Pendula, and our speaker is Dr. Sayan Sir, Professor, Department of Physics, Indian Institute of Technology, Kharagpur, India. And you can see his educational background and postdoctoral experience. He has completed his bachelor degree from Vishwabharati, Shantiniketan, MSc, Indian Institute of Technology, Kanpur, and PhD from Kanpur, Indian Institute of Technology. And his thesis title is Geometry, Matter, and Wave Propagation in Lorentzian Wormhole Space-Time. Thesis advisor, Dr. Dashdeep Shahadev. We can see his areas of research interest: general relativity, modified gravity theories, including physics of gravitational waves, strings and branes in flat and curved spacetime, Ricci and other geometric flows, quantum mechanics, tunneling, instantons, bounces, exact solution, classical mechanics, waves, and optics. We can see supervised. He also supervised many students, and we can see some of those students' title in PhD, and some of his research project sponsor. So thanks all for applications. Now it's time to go to our speaker. So sir, thanks again for accepting our invitation, sir. It's your time, sir. You can start your session, sir.
Yes, so my slides are already shared. So can
Yeah, yeah,
everyone see it?
yes, sir. We
Can,
can see, sir.
can everyone see the slides? Is it moving? Can you see it
Yeah,
moving?
yeah,
Okay.
we can see, sir.
Okay, so let me first thank Dr. Pretam Kumar Das for
It's my pleasure.
inviting me to give this lecture to the students of Pabna Institute, University of Science and Technology. It would have been nice if I were there physically, but as all of you know, it is not possible at the moment. So we have to connect virtually, and this has become our practice over the last 9 to 10 months,
And
where we essentially connect with our friends virtually and try to establish our relations and our correspondence with them. So Dr. Das wrote to me quite some time back, and that time I was actually giving several webinars in various places in India, and he requested me to give a talk which is based on basic physics, essentially to sort of motivate
yeah,
young students into doing something or learning some physics through simple examples, illustrations, and things like that. So what I have done is I have prepared a very elementary talk. So this you could think of it as an evening talk where you have some fun with physics. And as you can see, the title is Physics with Springs and Pendula. So there are a lot of things that you can do, and a lot of very important concepts in physics also can be illustrated through very simple examples, through springs and pendula. So that is the goal of the talk, and the entire talk is based on the basic notion, the notion of oscillatory motion, and that is what is the fundamental idea which is encoded in springs and pendula, physics with springs and pendula. So let me start by discussing springs as such. When all of you have seen what springs are, when they are there almost all around us, in from the simple ballpoint pen where you have a spring, to springs in cars, in the seats of cars, to springs in washing machines, to springs in toasters, and so on and so forth. So they are everywhere all around us in various situations. And the basic law that governs the physics related to springs is what is known as Hooke's law. So this was discovered or proposed by Robert Hooke, or understood by Robert Hooke many, many years ago. And the law is very simple, and all of you know it. It is something that is known to everyone. So there is a spring, there is a mass over here. There is something called a spring constant, and you write this relation F equal to minus K times X, where X is the displacement from its rest position. K is called the spring constant, and this is what is known as the restoring force. So if you use Newton's laws of motion, then you write F as equal to mass into acceleration, and from there you can find out the nature of the motion of a spring, of a mass m attached to a spring. So here the quantity K that you see over here is what is known as the spring constant. And we know that mechanical energy is stored in the springs. But the question that we ask now, which is important for us for the next few slides, is what is the value of K, or how do you find out the value of K? So from this equation, you can say that if I know the amount of force that I impart to set the mass m into oscillatory motion, and if I know the displacement x from its rest position, then by dividing F by that displacement, I can know what is the magnitude of the quantity K, which is called the Spring's constant. So this spring constant, of course, appears in the so-called omega, which is the angular frequency. The omega over here, as you know, is related to the square root of K over m, and the motion, as you know, is given by the simple case of x equal to x naught cos omega t. So the idea is that if you know what is omega and if you know the mass of the object, then you can find out what exactly is the value of K. So if you know m and omega, you can find K. So similarly, you can do a simple problem. You take a spring below a car's seat. Now, if a person of weight 70 kg sits on the seat and the seat location drops by 1 centimeter, you can figure out what is going to be the spring constant of that spring which is attached to the car seat. And there are several springs normally attached to the bottom of a car seat, so that when you sit down, then there is a depression, And the amount of that depression is dictated by what is that spring constant. Okay. So as I said, there are springs in everyday life, and I told you about the spring that you have in your ballpoint pen, the spring that you have in electric toasters, which make them jump up, the spring that you have in mattresses, in bicycle and car seats, in door closers, in washing machines, in various toys, and so on and so forth. And as I told you earlier, springs store the mechanical energy. Now the question is, and this is the important question related to the spring constant. The question is which spring to use where? And the related question is how to make a spring of a given spring constant. So we want to address these two questions, that is, which spring to use where. And to answer that question, we must know that how do I make a spring of a given spring constant. For instance, the value of K, the value of the spring constant in ballpoint pen springs is around this, 250 Newton per meter. The unit of a spring constant is Newton per meter. Similarly, for car springs, it is about 10 to the power 5 Newton per meter. So how does one make a spring as required? That's the question. And to answer that question, you obviously need to know what does this K depend upon. And of course, it depends on the material with which you make the spring. It depends on the diameter of that wire which you use to make the spring. It depends on the spring cross section, which is usually circular. And it depends on the number of turns. So these are the four things that are necessary to understand what K depends on. The material of the wire, the diameter of the wire, the spring cross section, and the number of turns. And therefore, depending on the values of the various quantities which are related to these four, you could tune the spring constant. Okay. And this is a formula which is known as the engineer's formula, where the spring constant is given in terms of the various quantities. So the material property appears in what is called the shear modulus, the shear stress by the shear strain. That is capital G. Capital D is the diameter of the spring. Small d is the diameter of the wire. And capital N is the number of turns. So now if you want to make a spring of a certain value for the spring constant, you can make it according to your choice, because you have to choose a material with a certain specific G, and you have to have a D and a small d and an N. And if you just choose your values appropriately, and you have various ways of doing it, you can make a spring which would work in the context where you're going to use it. So you can make springs according to your choice. Now you can ask me whether I can derive this formula. That's not difficult. You can derive this formula basically using the energy stored in the spring. And there are, if you just search a little bit in the internet, you will find out that there are many, many derivations of this so-called engineer's formula for the spring constant. So now I have a handle by which I can actually find out, or I can tune the value of K depending on these various quantities and the values I have chosen for them. And I can figure out the K that I desire for the situation that I want to use it for. And that is essentially the job of an engineer. Okay. So for instance, this capital G that you have, this capital G has units of gigapascal, Newton per meter square. For instance, the value of capital G for copper is, the material copper is 45 gigapascal. The value of G for aluminum is 26, around 25.8 or something, 26 gigapascal. And you can do this little exercise. You take capital D to be 2 millimeters, small d to be zero 0.2 millimeters, and capital N to be 10. And you can find out what is K for such an aluminum wire. And if you find it out, if you do this little calculation, you can see that such are the values for which you can make them useful in ballpoint pens. Okay, so what I'm trying to say over here is that whatever physics is involved in Hooke's law is not enough to tell you ways and means by which you can actually make a spring. So you have to move a little beyond that. And that is the reason why I gave you this engineer's formula. And this engineer's formula is actually telling you how you can make a spring according to your choice for the situation. For instance, a spring in a ballpoint pen would require K, which is different from a spring used in a car seat or in a bicycle seat or in a washing machine or in a toaster. All of these are basically related to the K that you need in order to get the desirable effect. In fact, what is the loading that you give and what is the displacement that you get tells you what is the K that is desired. And from that, you can actually figure out how to make a spring by choosing the right material with the right G, and of course, having these geometric features that capital D, small d, and N. So you can check the dimensions of this. You know that K has dimensions of force by length, right? And if you check this out, this also will have dimensions of force by length. Okay, so the message that I'm trying to give you in this, so you can do this little calculation and figure out various examples. But the message that I'm trying to tell you in your, among students in engineering as well as science, is a larger message. And that is the following. If you just have Hooke's law, the physicist may stop and say that I have told you what happens if you have a mass attached to a spring, and you know it's going to oscillate with a certain frequency. But then, what does the engineer want to do? The engineer want to make the right type of spring for use in a given context. And there are various situations and applications where you will need specific springs with specific spring constants. Now, in the process of doing this, the engineer may arrive at a formula which could be entirely empirical, in the sense that it doesn't have a theoretical basis. Of course, the formula that I wrote down does have a theoretical basis for K, but it may happen that the engineer may find a formula just by playing around with various experiments related to not just springs, but for various situations as such. But that formula may require an understanding by a physicist as such. The physicist then has to explain or derive it, or maybe generalize it or change the law also. Okay, so there is no conflict between the physicist or the engineer as such, and no one is greater than the other. What is happening is that there is an approach which is followed by the physicist, and there is an approach which is followed by the engineer, and the relation between them is, in simple terms, what is called symbiotic, in the sense That it's like a cycle. The cycle goes on. Science feeds engineering, engineers ask questions for science. And it is the perfect harmony between the scientists and the engineers which leads to the development of various important technologies as well as important laws that are uncovered in the context of science. So, for instance, if you go to a very big situation, like for instance, the particle physics experiments of the Large Hadron Collider, which many of you may have heard, or the LIGO experiment for gravitational waves, all of these require a perfect harmony in the workings of scientists, a large number of scientists and large number of engineers, and one actually feeds the other and vice versa. And in the process, we actually learn new things and newer developments in technologies as well. In fact, the internet that all of us are using nowadays was actually first proposed and used in the context of particle physics in CERN, where it's all of it began. So therefore, this is the message that I would like to give you, that it's a perfect symbiotic relation, and you can see it from the very simple example of the spring constant. That's a quantity which appears in Hooke's law, which is a contribution of a physicist. But that quantity, when you use it, when you need to make springs of specific values of k, you need to know what k depends upon, and that is the engineer's formula. And from that engineer's formula, you can actually make springs dependent on the situation that you have in hand. And that really teaches you a lot of new things as such. Okay, so let us move ahead from here and let me go to the mathematics here. Now, usually springs that we deal with, as I said, there is a cross section of a spring, and that is helical. So it's a helix that you see over here. The spring is geometrically or mathematically a helix. Now you can ask, how can you make a helical spring? And it's very, very simple. You take a pencil and you take some wire. You wrap the wire around the pencil, go on wrapping it, and then take the pencil out. And what you get is a helical spring. So that is my choice. I have said that the cross section is a circle. That's the simplest example, but there are springs where the cross section is not a circle. And of course, then that's a helix, but that's also not an helix which has a circular cross section. So how do you describe a helix mathematically? That's the next question. So you must be having a mathematical equation. So this is the picture of a helix. And you have this x, y, and z coordinates. And t is a parameter, and you have to write x, y, and z such that you can draw a curve in three-dimensional space, which is given by this curve that you can see over here, which is a representation of the helix in mathematical terms. And that's the equation that you can write down for x, y, and z, and that is going to give you the helical spring in mathematical terms. So there is something called the pitch. So what is the pitch? It is the distance moved along z. So z is this direction. So this is the z direction. So the distance moved along z as t goes over an angle 2 pi. You go round once by 2 pi and you move a distance p, and that is what is called the pitch. So if you have a small pitch, then you could have a larger number of turns in the spring. And depending on your choice of the various quantities like A and B, you could actually figure out the geometry of the helix and use mathematics to understand the geometry of a spring. Okay, so let me move ahead further and let's talk about optics with a helix. And this is actually very interesting. So suppose you take a spring and you put it up like this over here on a stand. And what you do, you take a helium neon laser and you shine that red light on the spring. So you can see this part is illuminated by that helium neon laser. Now, if you do it carefully and correctly, you would get a diffraction pattern. So what is that diffraction pattern? That's this cross over here. So you see a cross, and there is this angle alpha with respect to the vertical over here. So you note the cross with the gap. So these are essentially the dark regions or the diffraction destructive interference regions, and of course the rest are the constructive interference region. And you can find out, you can actually calculate what is the diffraction pattern that you would see on the screen, which is produced by nothing very, very difficult to get in your lab, but just a ballpoint pen spring. You just take it, put it up on a stand, shine a laser light, and you would see that cross pattern on the screen. So this is there in a nice paper by Thomson et al. A couple of years ago in American Journal of Physics. But then there is more to this. You know that DNA is a double helix. And in 1952, using X-ray diffraction, Rosalind Franklin and Raymond Gosling, these people who studied diffraction patterns of DNA, they found a diffraction pattern. There's a famous picture called Photo 51 of 1952. And what do you see over there? There you see the cross again. So it's again a cross over here. So you see the similarity that you got in the earlier picture that I showed you, where I just merely did a diffraction with a helium neon laser. I shone the light on that spring, which was held erect on a stand, and I got this cross. And many years ago, of course, in X-ray diffraction, you also got that cross over here. So that's a picture of a double helix, as you can see. So you see a similarity. And the similarity is, of course, related to the helical structure of the spring and the helical structure in a DNA. So you can see this wonderful similarity, and therefore you should be able to understand that there is a grand unity in various phenomena that occur which are related to physics. And you can see that what you see over here in this very simple experiment is not very different from what people had seen in X-ray diffraction of DNA. And that's because of the geometric structure of the double helix and because of the geometric structure of the spring, which is also helical. Okay, so let me move ahead. What we were talking about were real springs. So now you would think of imaginary springs, which are not really there as such. But what is there is the spring constant, an effective bond strength in diatomic molecules like carbon monoxide, hydrogen, HCl, and so on. So what do you have over here? You have these two, M1 and M2, and you have a spring, which is not really a spring in the real sense of the word, that you don't have a spring stuck there. But what you have is an effective bond strength, which can be modeled as if there were some kind of spring sitting there. And that's why I call them imaginary springs. Now, in your job, essentially, is to find out that bond strength. So how will you find it out? You will have to find it out through what are called molecular vibrations. Now, of course, you cannot observe molecular vibrations directly. So, what you do is that you have to do various kinds of experiments such that you can figure out the molecular vibration frequencies. And those are related to that bond strength, which is also a spring constant, but not of a real spring, but of some kind of an imaginary spring. Okay, and of course, there is the Raman effect where you can shine light of a frequency nu naught on the material. You know there is inelastic and elastic scattering. You observe the frequencies of the scattered light, and they depend on nu naught as well as nu m. And one can find nu m from scattering data. This is something which experimentalists in condensed matter physics do. And hence, what do you find out eventually? Eventually, what you find out are essentially the spring constants. Spring constants of what kind of springs? These are, as I said, they are not real springs, but they are effective or imaginary springs. For instance, for the carbon monoxide molecules, you have K is equal to something like this. So you see, where have I started out with a mundane spring where there was a mass and a spring and simple oscillations. Then I moved to the engineer's formula. And from there, I again moved away. And I told you about the mathematics of the spring, which is a helix. And then I told you about optics. And then finally, I told you about imaginary springs. So you see, there is a whole range of physics, chemistry, maths, whatever, which are related to this very elementary idea, which is that of a spring constant. So there is a grand unity. And that is why Hooke's law, for instance, is fundamental and so important, because it is the basic foundations on which a large number of phenomena can be understood and explained. Okay, so let me now move away. So as I said, springs relate to what is called oscillatory motion. Right? So you get oscillatory motion, and that is the fundamental consequence in terms of motion with in the presence of springs attached to masses. So now what I'm going to do is I'm going to give you 3 simple examples of oscillatory motion, and 2 of them I will show small videos at the end of the talk, not now, because I don't want to disturb the flow of the talk. So what I'll do is I'll do these 3 little examples, and the first example is something very intriguing which you can do yourself. But don't set things on fire. This is called the candle seesaw. And this was there in a French magazine in 1893, La Science Amusante, where what you see is if you take a candle and you prop it up at its center of mass, like this over here, and you light both ends. Now, if you light both ends, a remarkable thing happens. There is an oscillation of the candle. Okay, and it persists and it grows. So if you try to see what is that experiment, a more technical experiment has been done, and it's there reported in this nice article, which you also can sit down and read, where you can observe the nature of the oscillatory motion that you see. So this is what is called the candle seesaw. And I'll show you a video at the end where you will see that the oscillations actually grow in time. So what happens? Suppose you have an unlit candle and you get it started. Obviously, it will oscillate, but what is going to happen is the oscillations will gradually die down, which is what you see over here in this case. But if you light both ends of the candle, then you see something strange. what you see is that the oscillations tend to grow with time. And this is a very simple experiment which you can do yourself, and you will find you will amuse yourself by doing this experiment. But it is not something which is very easy to actually explain in theoretical terms. Because what you see on both ends, when you light both ends, the wax in the candle melts. And you have to take into account that melting rate of the wax on both ends. And it is that which essentially is a difficult task. And from that, you can actually figure out, using simple mechanics, of course, that you will get growing oscillations and you'll get a candle seesaw. So this is one example of oscillatory motion, which is very interesting and which can actually tell you a lot more about physics of oscillations. Then, of course, there is this example of a fluid rising. You have a straw over here, and you have just a simple tumbler where you have a liquid. So if you put the straw in and you press your finger, then you will see this rise a little bit. And then you remove your finger, you will see oscillations over here, which are going to be damped oscillations. So they're going to go up and down like this. Okay. And that's the picture that you can see over here. So this is the fluid level. The fluid level is going up and down, and you can see damped oscillations. So you can build a model based on Newtonian mechanics, or there's another model. The basic physics of the model is just the fact that there is a gravitational force, there is a pressure force, and there is a damping force. And if you solve this equation with appropriate models for each of these, then you can model the motion of the surface of this fluid inside the straw and its oscillatory motion. So this is also some experiment that you can do very easily. Just you can find out the time dependence of the height over here. Okay, using a simple mobile camera as such. And once you find out how this height changes with time, you can plot it. And from there, you can figure out what is that oscillatory motion. And then you can follow the model. You can look it up in this paper by Smith and Matlis, also in American Journal of Physics. And you can learn a lot about oscillations from this. Okay. So let me move ahead with another one, which is something that you may be familiar with, which is called the gravity train problem. And in this problem, what you do is you dig a tunnel through the Earth's center to a diametrically opposite point. For instance, two diametrically opposite points are essentially Hamilton in New Zealand and Cordoba in Argentina. And suppose you imagine you put a tunnel over here. Now, if you put a tunnel and you look at the motion of a small mass in this tunnel, you know that it will oscillate. And what is the frequency of that oscillation? That's given by these very simple. This is a very simple problem which is done in more largely in high school as well as in first year physics, where you can figure out what is the time required to make the mass go from one end to the other, and it turns out that's 42.2 minutes. So this is what is called the gravity train problem, and there have been lots of work on this. And for instance, in this reference in 2015, you will find a model where you don't take into account the constant density of the Earth, but a varying density of the Earth. And there is a profile for that density, and depending on that, you calculate what is the time taken by a mass to go from one end to a diametrically opposite end. So once again here you see that you have oscillations, you have oscillatory motion. So I've given you 3 examples over here, all of which deal with oscillatory motion: the candle seesaw, the fluid in a straw, and the gravity train. Okay, now let us move on to the last topic, which is about pendula. Okay, so all of you know what is the simple pendulum. It's said that it was discovered by Galileo around that time. And this is the picture of a pendulum. You have a massive bob, you have a massless rod, you have a frictionless pivot, and theta is basically the displacement angle from the equilibrium position. And you know the time period is twice pi root over L by G. And the trajectory is essentially that of a simple harmonic motion. Okay. Now you say all of you are familiar with the fact that to get simple harmonic motion, you must have small theta. So you take theta equal to 30 degrees, not equal to, this is a mistake. Theta equal to 30 degrees equal to pi by 6. And you say sine theta is equal to half. So it's 0.5, but you take theta equal to pi by 6, that is 22 by 42, which is also 0.524. So sine theta is equal to theta for even when theta is equal to 30 degrees. So what is happening? You're familiar with statements in books where theta has to be some 4 degrees or less than, but now I have shown you for theta equal to 30 degrees also, sine theta is equal to theta. So what is going on? Well, that theta equal to 4 degrees is not something which is sacrosanct as such. It is certainly true that you get simple harmonic motion for small angles. There is nothing wrong in that as such. But one needs to know the error while approximating sine theta using theta. So that is the crux of the whole issue, that one needs to know the error while approximating sine theta using theta, and that's going to decide for you where your linear approximation of sine theta as theta is valid. So this myth about theta 4 degrees is something which is probably just empirical, in the sense you don't get if you give a large amplitude initially, then of course it can happen that it can sway and it can wobble and so on and so forth. So that's probably the reason why people say that you give small angles, but mathematically it's basically the error when you approximate sine theta with theta which has to be taken into account. Okay, so that's a little statement about small theta approximation and pendular motion. Let me now go to another question. And suppose I take more than one pendulum. So I have 2 pendula with different initial conditions. So what I have is, I have one pendulum starting out with x naught and velocity u naught, another pendulum starting out with x naught plus delta x and u naught plus delta u. And obviously, if you leave them, what is going to happen? They are going to strike each other. So I have considered 2 identical pendula set in motion with initial t equal to 0 conditions at x naught u naught and x naught plus delta x, u naught plus delta u, and you ask this question: when will they strike? Well, the first trajectory, the trajectory of one of the pendula which started out at x naught with velocity u naught, is going to be given by something like this, which you can mathematically solve. It's very straightforward. X equal to a sine omega t plus b cos omega t, and use your initial conditions at t equal to 0 to get this expression. Similarly, for the other pendula, you will have x naught plus delta x and u naught plus delta u. And obviously, if they two hit each other, then x1 at tf has to be x2 at tf. So tf is what is called the meeting time. And that is found out by just equating these two at tf and you will get a relation which is something like this. So this time depends on omega and the ratio delta u by delta x at t equal to 0. And one can have many trajectories or many pendula with the same ratio delta u by delta x, but with different large delta u and large delta x as well. And all of them would meet at TF from this very simple two-line calculation. So what have I found? And you will see why I am doing all this, because this has a broader context. Okay. So you can think of theta t as a new variable, not the theta of the angle of the pendulum. Here x represents basically the angle. I have taken L equal to 1 and M equal to 1 and so on. So x equal to L theta, so L is 1, so x is like theta. So this theta t is not the angle, but a new variable which is related to delta u by delta x. And if you write down the function theta t as given by this, you can show that theta t satisfies an equation of this kind. And look at the denominator. The denominator tells you that theta t is going to go to negative infinity when the denominator goes to 0. And what is that denominator? That denominator is exactly the same as this condition. Okay. So therefore, here I have said that at t equal to 0, theta is equal to theta naught. And theta t satisfies an equation like this. And theta t will go to infinity. So this is a new variable which actually goes to negative infinity at the time when the two pendula or the many different pendula are going to strike. Okay, so this is a new equation, a new variable and a new equation for essentially a collection of trajectories which start out at a given value of delta u by delta x. So I'm looking at many trajectories of the same system, which is simple pendula, and I want to find out where those trajectories are going to meet. And I have a new variable theta t, which actually tells me this theta t is a solution of this equation that I've written down over here. And all of this can be generalized. I'm not getting into complications. So you have a new variable theta t, which tells you about, in fact, the divergence to negative infinity of theta t is at a time when the true trajectories are going to meet. And 2 is not sacrosanct. You can have as many trajectories as you want, and they will all start out with a negative theta naught and will eventually diverge to negative infinity when t goes to tf, and that tf is given by this relationship. Okay, so I have given you a new problem. I have told you about a new variable, and I can do a little bit of plotting over here. I can find out what is tf as a function of theta naught. What is theta naught? Theta naught is the initial value of the ratio delta u by delta x. You can have different delta u's and different delta x's with the same delta u by delta x. Similarly, you can plot theta t versus t, and you will find that they are going to go down to negative infinity as the two pendula hit each other. Okay. So the meeting of trajectories, so if you draw the individual trajectories, there are various different trajectories, and you can see that they come and meet at this point. Okay. So now let us do a huge extrapolation. So what is that huge extrapolation which I would like you to do? Now you think of trajectories of galaxies in the universe in time. Okay, so if you think of galaxies as points, that is what cosmologists do. So if you know how these galaxies has evolved as the universe has expanded, for instance, you know that the galaxies are all moving away from each other. So you ask the question, what happens as we go backwards in time? So they would essentially be coming closer to each other. Similarly, you can think of a bunch of objects which are falling into a black hole where there is a very strong gravitational field. Now, how do these trajectories of these objects which are falling into a black hole look like relatively as we go closer to the black hole? So they will come closer to each other. When you go backwards in time, the trajectories of these galaxies, for instance, are going to come closer to each other and they're going to hit each other at the Big Bang. Similarly, the trajectories of objects which have been thrown into the black hole, which basically are going to hit each other at the black hole, which of course you cannot enter or see, but you can only imagine, and they will meet at the so-called singularity, where there is an extreme gravitational field at the black hole. Okay. So, in the Big Bang, for instance, we live in an expanding universe. Each galaxy in our universe is moving away from each other. So, we know that from Hubble's law. If we go back in time, the galaxies will be coming closer to each other. And therefore, the trajectories will meet at the Big Bang, which is something very obvious. Now, it's the same thing when if you have two pendula which strike at a finite time, their trajectories also meet. Similarly, all galaxy trajectories will meet at the Big Bang. And same way, all trajectories falling into the black hole will meet at the black hole, where there is a strong gravitational field. So what is happening? You have, when you go backwards in time, in a cosmological constant, you go to smaller and smaller volumes, and you go to denser and denser situations in terms of density of the matter that is there in the universe. And the ultimate situation is the Big Bang, where all these galaxy trajectories are going to meet. Similarly, the ultimate situation here is the black hole, where all the trajectories which are falling into the black hole will meet. So the attractive nature of gravity tends to draw things together, and this is a phenomenon which is called, in analogy with optics, called focusing. Now, the proof of this is actually a generalization of an equation that we wrote down for theta t. And this is called the Rai-Choudhury equation, which was discovered by Amol Kumar Rai-Choudhury in 1955. And this equation is fundamental in proving what are called the singularity theorem or results on singularities in relativity. There's an I missing over here. It's results on singularities in relativity. And all of you know that Penrose won the Nobel Prize, half of the Nobel Prize in physics in 2020, for proving the first such result, which essentially uses the consequence which are based on the Rai-Choudhury equation. So I have told you that how from a very, very simple example related to oscillations as such, you can go to a broader context and you can understand or at least appreciate the basic ideas behind which the results, the mathematical results of Penrose and Hawking rely upon. Okay. Okay, so what I've shown you in this talk is something, as I've been emphasizing, there is a grand unity in various different phenomena, and the paradigm which we talk about is related to oscillations. We started with Hooke's law, we talked about the spring constant, we gave the engineer's formula, we looked at applications of what kind of Ks are required for what kind of springs and how do you engineer specific springs for specific situations. Then I talked about the mathematics of a helical spring and I talked about the helix geometry. Then I moved to diffraction by a spring, and then I saw that diffraction by a spring has a cross, which is the same cross that Rosalind Franklin and Raymond Gosling saw when they looked at the diffraction of DNA, which incidentally is also a double helix. And then I went to imaginary springs, which are bond strengths, where I measured K, and I told you a little bit about the Raman effect. So this gave me or led me to oscillations, and I gave you three simple examples of oscillations: candle burning at both ends, fluid in a straw, and the gravity train. And then I talked about pendula, simple pendula, several pendula. Then I looked at the striking time, the initial conditions, and told you about the Raychaudhuri equation, the Big Bang black holes, and what I did not tell you about what would happen if there are many coupled pendula. And that's going to give you wave motion. And when you have quantization of those waves, that basically gives rise to quantum fields. Okay. Okay, so concluding remarks. What I have done is I have tried to relate the apparently unrelated. What I mean by this is you see the broad spectrum which arose when I talked about springs, starting from the engineer's formula to the diffraction by a spring to the DNA to the imaginary spring. That's a whole spectrum which apparently look unrelated but are actually related. So you see a unity among various diverse phenomena. And there is a single concept, oscillatory motion, and you see novelties and logical extrapolations. And I've told you about doable experiments in undergraduate labs with easy theory as well as open questions and links to advanced topics. And that is essentially what is the scientific attitude and the scientific temper, which I believe all of you follow as you learn your science and engineering. Okay, so I will just end by showing you a few videos which will basically tell you or show you some of the illustrations of some of the various topics that I talked about. So the first of them is that fluid in a straw. Okay, so the fluid in a straw. So what I have to do is let me just open it separately,
Sir, you
and
have to share your screen again
I have to share
with
my
Enter
screen again. Yeah, I have to share my screen again with the video. Yeah. So is it visible?
Yeah, we can see now. Okay, so that is the video for the fluid in a straw example. The other video that I would like to show you is this one.
Today, I'm going to show you how to make a really cool candle seesaw. Perfect if you're bored and looking for something to do. Start by taking a candle, then using a sharp knife, carefully remove some of the wax from the bottom of the candle to expose the wick. It should look like this. Next, roughly work out where the balancing point of the candle is and put a mark in the wax. Then take a needle, grip it firmly with some pliers, and use a lighter to heat it up.
Okay, so I will share this other video that I have, which is about the flaming.
Dear student colleagues, we have disconnected with our speaker, so we're trying to connect with our speaker. So sorry for that. Please stay with us.
Got disconnected a little bit. Yeah, so let me just try it out once more. So anyway, it is getting disconnected for some reason. I don't understand this. Can you hear me?
Yes, sir, we can hear. Maybe there is some technical
So
problem.
let me just try it out once last time.
Today, I'm going to show you how to make a really cool candle seesaw. Perfect if you're bored and looking for something to do. Start by taking a candle, then using a sharp knife, carefully remove some of the wax from the bottom of the candle to expose the wick. It should look like this. Next, roughly work out where the balancing point of the candle is and put a mark in the wax. Then take a needle, grip it firmly with some pliers, and use a lighter to heat it up. Then push it straight through the middle.
Was it showing? It was not showing, right?
No, no, no. I think you can choose your entire screen option while sharing
Yeah, yeah.
screen.
So let me just open this and then share. Anyway, I think you can see these videos. They are available in the internet, called the candle seesaw. So if you have any questions, you can ask. I think there are
Thank you,
students.
sir, for your nice presentation, sir. So I
Yeah.
think
So
students have
if
learned a lot
there
of
are,
things about the basic physics with spring and pendulum. So but thanks again for accepting our invitation. So we haven't got any question from a student, but this
yeah,
video will still remain in the Facebook and our group. So if
yeah,
anybody asks question, so I'll ask to you later. And
yeah.
thanks again, sir. And after the COVID, I will definitely invite you for a face-to-face session. It will be a very great seminar with you, and I'm very grateful to you for for giving me this opportunity to arrange such an important webinar, sir. Thanks again,
So,
sir.
yeah. Okay, fine. Thank you very much. I hope the students could understand something in the
Yeah,
talk.
it is very interesting talk, sir, and
Yeah.
I think it will be very helpful for not only for physics student but also for others, engineering student also.
Yeah. Okay.
And
So you can. So the point is, the videos. Unfortunately, the second one was not, because it was from YouTube. It was not
yeah,
visible.
yeah,
So I think you can see it if you wish.
yeah.
If you just give a search candle seesaw, there are lots of videos which will come out. Okay.
Okay, sir. Thank you, sir.
Okay then. Thank you very much. Yeah.
Yeah. Good
Thank
night, sir.
Thank you very much.
Bye.
Very nice. Very nice meeting
Yeah.
you all.
Yeah. Nice to meet you
Thank
too, sir.
Thank
Bye,
you.
sir.
Thank you.
No.
Thank you.